Hello everyone, and welcome back to another video where we are going to be deriving Coulomb's law from some field theory. We're going to be using the results from last Physics Friday, namely the Euler-Lagrange equations, some tensor calculus, and complex analysis, so really hitting on all my favorites today. So without further ado, let's go over a couple of our assumptions, actually. So the first one is just going to be number one, right here. Charge is just going to be conserved. So this is just saying the for divergence of our potential right there, or sorry, our charge is just going to be 0. 2 is just the Lorentz gauge right there. And 3 is just the definition of a point charge in this context right here. So now, for real this time, let's get on with some tensor calculus and some fields. The first term in our Euler-Lagrange equation you will see is this partial derivative of our Lagrangian with respect to the muth component of our vector right there. And you'll see that this actually isn't too terrible to compute. And the reason for that is because this F term right here, our electromagnetic field tensor, that right there, well, it's a function, or I say function of, the way it's defined is only in terms of the derivatives of our vector potential, not actually the vector potential on its own. So any partial derivatives involving that with respect to just our vector potential will be 0. So that means we only have to worry about the next two terms in our Lagrangian right here, so just those two right there. And we see that differentiating with respect to a mu, we end up with m squared and then a mu, and then minus j mu right there. And that right there is 1/2 of our Euler-Lagrange equation. Granted, it is kind of the arguably more boring half, though all still necessary. Now let's go on to the second half of our Euler-Lagrange equation. We need to differentiate with respect to partial mu a nu. And you see here that we have this right here, but squared. So what can really be helpful, actually, is evaluating this f squared term in terms of just a's and partial derivatives. So let's go ahead and do that real fast. So getting a special little bit right here. So f squared, f mu nu squared, this is really just a shorthand for f mu nu, and then f mu nu. I said the exact same thing twice, but there is a difference. One is covariant and one is has contravariant indices. But what this really means is that we're multiplying these two things together. So we have partial mu a nu minus partial nu a mu. And then we're multiplying that by partial mu, but in the upstairs this time, a nu, and then minus partial nu a mu. So what exactly do we get when we FOIL this out? Well, let's just go term by term. These first two terms, what do these give us? Well, they give us partial mu, a nu, and then I'm going to just put parentheses around here, and then partial mu a nu. But that right there, we can just write as, well, actually quite nicely, as just a shorthand. We can just say that this right here is partial mu a nu squared. Well, great. That's at least one of the four terms down. Now, what about the second one? Well, if we multiply these two last indices right here, or I say indices, last two terms right here, what we end up is plus, because the minuses cancel, partial nu a mu, and then partial nu a mu. We can just write this as partial nu a mu, and then squared, but because of the Einstein summation convention, we're summing over both mu and nu, namely from 0 to 3. So these right here are actually just equal to each other. So what we end up with is the same term twice, actually. So we can combine these two terms right here and say this is just equal to 2 times partial mu a nu squared. Well, great, we've taken care of half the terms. Let's go on to the other half, which are a little bit more interesting and a little bit more finicky. So our next two terms are going to be minus partial mu a nu, and then times partial nu a mu. So you see here that the indices are sort of the same, but they're completely flip-flopped. And what happens with our second term that we get here? Well, it's also going to be a minus, so I might as well just open parentheses here. Well, we're going to have that, and then just plus partial nu a mu, and then the other way around, partial mu a nu. So how exactly can we simplify this? Well, we can expand out some of these partial derivative terms. And what I mean when I say that is just use the fact that g mu nu of partial nu is just going to be equal to partial mu. So we can just change the letters around here appropriately. So for our example, this term right here, we can just express as, well, the outside bits aren't going to change. We're still going to have this. But then we can just have g and then nu mu, and then times partial mu, and then times a mu. And the reason we're able to use mu here is that we do just happen to be summing over it, right? So we do just happen to be summing over it. So we could very well just use like alpha or something, but for the sake of only using two letters, we can just use mu, because I mean we're still summing over it. It doesn't matter a whole lot. We're only doing a little bit of tensor calculus, so it's not the end of the world. And then this next term right here, we can do the exact same thing. So we can just have partial nu a mu, and then times, well, g mu nu, and then partial nu a nu. And what's one more thing we can do to kind of get all things in this form right here? Well, we can actually just raise the index of this a right here. So let's go ahead and do that real fast. Using the same rule as here, I'll just replace the partial derivative symbol with an a, really. So what this is equal to now is just partial mu, and then this a nu is equal to, well, it's going to be the same thing, but like flipped with the indices. So it's going to be g nu mu in the downstairs, and then a mu in the upstairs. And then we're going to have our g nu mu. And then we're going to have our partial derivative term, partial mu, and then a mu. And then we're going to have plus right here. I swear this all simplifies. And we're going to have partial nu g mu nu a nu, and then g, I'll zoom in on this part, and we have g mu nu partial nu a nu. And there's no parentheses there, actually. So what we get here, that's actually really funny. I closed the parentheses that didn't need to be there. So what we have here, you might see, is some things that cancel. And when I say cancel, I mean we have a metric tensor contracted with itself. And assuming we're just in flat space, you can move those outside of the derivative. And these right here are just going to cancel out to 1. And same thing with these right here. So what we're left with in total is just a partial mu, and then a mu, and then partial mu, a mu, and then plus partial nu, a nu, and then partial nu, a nu. You'll see that this is the exact same thing, especially because we're literally just summing over mu and nu. And from here, it's not too difficult to see that this is just equal to 2 times partial mu, a mu, and then just squared. But hold on. Let's go back to our assumptions right here. We're assuming the Lorentz gauge right here. So this partial mu, a mu term, that right there can actually just be simplified to 0. So this is really just, we're saying that that there is just 0. So what we're left with this entire thing is this term right here. So let's go and plug this into our Euler-Lagrange equation. We see that the partial derivative with respect to partial mu a nu, well, that right there, the only thing that's going to be non-zero are the terms inside of our f. So what we have then is partial Lagrangian, and then partial. That writing partial inside of partials, that always seems a bit odd, but that's cool. But this right here is just going to be the partial derivative with respect to partial mu a nu of, well, negative 1/4 and then times 2 partial mu a nu and then just squared. So actually taking the derivative here and simplifying the fractions, we see that this is just equal to negative 1/2, but we end up getting another 2 because of power rule. And then we just get partial mu and then a nu, which we can just express as, well, erase that bit right there, and we just get minus partial mu a nu. But wait a minute, we do have to take the derivative again. You see that in our Euler-Lagrange equations, there's another partial right there. So really, our Euler-Lagrange equations can just read the following. We just have m squared a mu minus j mu equals minus partial squared mu and then a nu. But one of the fun ways to actually write this, I always enjoy it when you're able to do this. You can write this partial mu squared term right here in terms of just the D'Albertian operator. So this is equivalently just negative box a nu, which is always fun. Using a box is always, I don't know, I always really like it. But anyways, let's go ahead and actually put together the equation we have. So given that our mu's and nu's are really interchangeable, at this point we can just rewrite this whole thing as D'Albertian plus m squared, and then that's acting on just our a mu, is equal to just j mu itself. And that right there is just the differential equation that we need to solve. And a cool thing here to note is that if j is just 0, we end up getting the equation for a free particle, really, or no potential at all, and it would just be the Klein-Gordon equation. I should note that we are using natural units, so h bar is 1 and c is also 1. But let's go ahead and actually go ahead and solve this, shall we? And the way we're going to do that is by substituting in this j right here, and then doing some Fourier wizardry. I say wizardry, it's just math. This right here is equal to just our charge q, and then times partial our three-dimensional Dirac delta of our vector right here. And you'll remember here that the only component of our potential, or our j right here, is just the 0th component. So, and we really only want to consider the 0th component of our vector as well, because that's going to be the Coulomb bit. So we're just going to throw in a mu right there. And then we're going to have plus m squared right here, of course, and then our D'Albertian operator. And now one critical assumption that we also are going to make is the fact that this right here is not going to be time dependent. That is, the partial derivative of this with respect to time is just going to be 0. So another way to actually represent this then is going to be as, well, negative our Laplacian right here, where that's just all the sum of our second derivatives, plus m squared, and then times a naught right here, is equal to q, and then this right here, of course. And what this allows us to do now is just solve this differential equation using Fourier transforms. So what we're going to do is take the Fourier transform of everything right here, and this is what we're going to get. On the right hand side, we're just going to get q itself, because we'll consider all pi's at the end, of course, but we just have q because the the Fourier transform of the Dirac delta function is just going to be 1. That would be a really good video in its own right. Coming soon to a ginger math near you. But then we have the Fourier transform of our Laplacian right here, and that right there is just going to be the absolute value of our k right here, plus m squared. K is the variable we're going to be using for our Fourier transform, and then we're going to have a tilde, a naught tilde, of course. So we can just solve for a naught tilde and do our inverse transform. So what this means is that a tilde naught is equal to q over k squared and then plus m squared. So how exactly do we take the inverse transform here? Well, what we're going to have to do is just consider the inverse transform formula. So our a naught is going to be equal to 1 over and then 2 pi all cubed, and then times an integral over all of our Fourier space right here of r a tilde, and then times e to the I, and then our x vector times our k vector right here, and then d3k over the entire Fourier space. Since we're taking this integral over the entirety of our Fourier space, we can actually represent it in spherical coordinates. So the way we're going to do that is, well, first by substituting in a tilde. So rewriting this, we have 1 over 2 pi all cubed, and then times, well, our three integrals right here. One is going to be from negative infinity to infinity. The reason why I'm doing that for our k right here is actually because the integral that we have is easiest evaluated with complex analysis, and integrals with all real numbers, with bounds of all real numbers in them, are a bit easier with complex analysis, which means that in our spherical coordinates, we're not going to have our typical 0 to pi, 0 pi. We're going to have just 2 0 to pi's for our bounds. So what that means is that we have, well, I'll throw the q out front of the integral because might as well. So then we have, well, k squared and then times sine of theta by our convention in spherical coordinates. We have k squared and then plus m squared times r e to the I, and then, well, x dot k. But let's really think about one way to express the dot product. We know that in general, if we have two vectors, so, if we have a dot b, we know that we can represent that dot product as the absolute value of a times the absolute value of b, and then just times the cosine of theta, where theta is the angle between them. And one way we can do that just here is by invoking that formula. So we can just take the absolute value of a, the absolute value of k, and then times cosine theta. So what that leaves us with is just, what's the absolute value of x? Well, if we also let x just be in spherical coordinates, it can just be some distance r from the origin. So, just r right there. But then we also have the absolute value of k. And how far is k going to be from the origin? Well, we're also using spherical coordinates, so that's just going to be k. And then we have our cosine of theta. And then we have our d phi, d theta. The order of there doesn't matter because the bounds are the same. So, and then we have our dk. Well, so how exactly do we evaluate this? Well, we can just do a quick little substitution. We can just say that u is equal to cosine of theta, meaning that our du is equal to minus sine theta, and then d theta. So this means that our integral with our thetas right here, so it's just going to become the integral from -1 to 1, just using that minus sign to flip the bounds of the integral, of just, well, I'm only going to include the terms that concern thetas here, and we'll throw everything back in the big integral in 1 second. The signs are just going to cancel. So we're left with I, and then times r k, and then just u, du. And what this equals right here is just going to be 1 over I r k, 1 over irk. That makes me angry. No, I'm kidding. This right here, and then just times e to the I r k, and then minus e to the minus I r k. So subbing this into our entire integral right here, this is what we're going to get. We're going to have, well, still one, I say one, we're still going to have q over 2 pi all cubed, and then we're going to have our integral from negative infinity to infinity, of course, and might as well evaluate the phi integral out front. I mean, they just throw a pi right there, because 0 to pi, not 0, nothing crazy right there. But what we have then is a 1 over I r k, and then times k squared, and then e to the I r k minus e to the minus I r k. And then we're going to have our good old 1 over k squared plus m squared dk. And all we have to do now is evaluate this nice little integral right here. And the way we're going to do that is first actually by simplifying them. We'll just go ahead and exploit symmetry. So throwing some stuff onto the outside, we have a q times pi over 2 pi cubed. I'll simplify that in one moment, but we'll have an I r out front. Then we have our integral over all real numbers of just 1 over, or sorry, well, k, and then over k squared plus m squared. And aha, you might think, it's just 0, but not quite actually, because this e terms right here is an odd function as well. So this function here is even, actually. This is an e minus irk dk. Now there's a very important thing about this integral we need to point out. So what I'm going to do is split this up. So we're going to have the integral over all real numbers of k over k squared plus m squared, and then e to the irk dk, and then we're going to have just plus the integral over all real numbers, and then times negative e to the minus irk times k over k squared plus m squared dk. And on this second integral right here, what I want to do is just do a simple substitution. I want to say u is equal to just negative k. And what happens when we do that? Well, not a lot changes actually, because, well, we're going to have the integral from, it's going to be a lot of minus signs to keep track of, but let's just go ahead and do it real fast. Those are our bounds, and then we're going to have an extra minus sign up front because of the dk and the du. And then we're going to have a minus e to the positive iru. And then we're going to have a minus u out front right here. And then we're going to have just a u squared. And then plus m squared right here. Du. And notice here that these two minus signs cancel, and we can just use this minus sign to change the bounds. And what we're left with is the exact same integral as this right here. So in fact, our integral, this right here, can just be expressed as q over 2 pi squared, because we had an extra 2 out front, right? And then times the integral over all real numbers of k times e to the I k r over k squared and then plus m squared dk. So now all we have to do is evaluate this integral right here. And this, ladies and gentlemen, is where the complex analysis shines, and we get to do some contour integration with physics on a Physics Friday. This is wonderful. So we're going to be using our usual semicircular contour, with there's going to be a pole at mi. So let's just go ahead. By Jordan's lemma, we know that the outer semicircle is just going to go to 0. So this right here is just going to be equal to 2 pi I, and then times the residue just at mi. But let's find the residue at mi real fast. Well, if we just go ahead and we can just really just plug in mi, well, I say plug in, I guess find the limit really. So we have k minus mi over k squared plus m squared, and then times, well, k, so times m, well, k. I keep substituting stuff in too fast. Times k, and then times e to the I k r. Then the limit as k approaches mi. And what this right here equals, factoring out the denominator, and canceling a couple things, is just mi, so that k, times e to the mi times I times r, so minus mr, and then divided by 2mi. Considering that's a residue, what we have then as our answer is just the following. We have a q over ir times 2 pi squared times 2 pi I times e to the minus mr, and then just divided by 2. So what do we get when we simplify all of this? Well, you'll see that, well, these two's cancel, these i's cancel, so thank goodness we're left with something real. And then you'll see that this pi and one of these pi's here cancel. So what we are left with is a q over 4 pi r, and then times an e to the minus mr. And you'll see here that we're not actually left with Coulomb's law. We're left with the potential, but for something else. And what this is for is the Yukawa potential. It's really a model of, one of the first models of a nucleus of an atom. and it's where the mass right here contributes to the potential. So if we just kind of go ahead and take the limit as mass goes to 0, you'll see that we're actually left, so the limit as m goes to 0, we're just left with Coulomb's law. So this gives us just q over 4 pi r. And that right there, ladies and gentlemen, concludes our awesome adventure to finding the Coulomb potential, which just to differentiate, find Coulomb's law from it. But at any rate, I really hope you enjoyed this video, combining a lot of my favorite subjects, and I hope to see you all in the next Physics Friday.